So again, folks, we're looking at our discussion of the library of functions. These are the functions that you want to have memorized. You want to be very familiar with them. And the reason for that is because we build all of our other function work and all of our other graphs off of these 8 or so library functions. So the one we want to look at now is the square root function. And again, I have the graph memorized. Without needing to plot any points, I know that that's what the graph of the square root function looks like. Now if I want to be more careful, I can build a table of values. We could take x and find f of x. If I plug in 0, the square root of 0 is equal to 0. If I plug in 1, the square root of 1 is equal to 1. If I plug in 2, the square root of 2 is approximately 1.41. That's not maybe a good value to plug in on the graph of this function. In fact, I think it makes sense to pick perfect squares. Now those aren't the only points on the graphs, but they're the ones that are easiest to work with on our square root function. And so if I plug in a few of these points, we're able to construct the graph of our square root function. From the graph, we can see that the domain is from 0 to infinity. If I project the domain down here into the x-axis, we see it's 0 to infinity. Or from the graph, we can see that the range is also 0 to infinity. But I think it bodes a bigger discussion. This is one of our problematic operations. You can only take the even root of non-negative numbers. Or put another way, the square root of a negative number is not real, and we're not considering the non-real numbers at this point. This function is increasing. We've talked about what that means. It's increasing on 0 to infinity. I don't want to get into what's happening at 0 at that boundary point, but we would say that in general, as you go from left to right, the function is increasing. That's the hallmark. So let's say it like this: as x goes to the right, f of x is increasing. This function is neither even nor odd, and we see that because the domain doesn't allow me to plug in the opposite number. So while f of 4 is equal to 2, f of negative 4 is undefined. So it's neither even nor odd, and it has no symmetries either. Let's look now at the cube root function. So what I'd like you to do is, again, pause the video and try to sketch the graph of the cube root function. If you need to, go ahead and plot some points, but this is again one of those graphs that we want to have eventually memorized. So pause the video and give it a shot. So here's the graph of our cube root function. It looks something like this. And this one's a little bit easier to describe in terms of its inverse function. If you were to take the graph of f of x equals x cubed, which we now know, the graph of x cubed looks like this, and you were to rotate that about the line y equals x, you will get your cube root function. So notice that I have this basic shape memorized. This is not the same, for those of you that have seen it, this is not the same as the arctan graph. It has no asymptotes, although if you said it has some similarities, I would agree with you. But this is not the graph of the arctangent. This is the graph of the cube root function. So let's go ahead and plot some points on here. The cube root of 0 is 0, the cube root of 1 is 1, and the cube root of 8 is 2. If we plug in some other points, the cube root of negative 8 is negative 2. So again, I did that kind of fast, but let's just say we plugged in 8. Then our functional value is the cube root of 8, which asks the question, what number when multiplied to itself 3 times gives me 8? And the answer to that is 2. And if we plug in negative 1, what number when we multiply it by itself 3 times gives me negative 1? And the answer is negative 1. And that's how I got some of those points on the graph of this function when doing a more careful sketch. Notice that oftentimes when we have a axes with an even scale, the graph's a little bit harder to see, which is why we as math people sometimes exaggerate the shape of that graph when we do our rough sketches. Notice that the domain of this function is all real numbers. I can take the cube root of any real number, including negatives. I guess I should include this, including 0. The cube root of 0 is equal to 0. So the domain, we can see, is all real numbers. The range, although it may take us a long time, is again all real numbers. Eventually, if I want to get up to this range value out here, I just have to go out far enough on the graph of this function and I'll find a point on it. This function is always increasing, and this is an odd function. We saw that, for example, here's the ordered pair -8, -2. Well, here is the ordered pair 8, 2. And so what do we say? We say that opposite domain values give opposite range values. That's what it means to be an odd function. And also it means that we have that symmetry about the origin. Let's do one more function for this page. Again, I'm going to encourage you to pause the video and sketch the graph of this function, so go ahead and do so. So folks, this is one of the last functions we want to make sure that we have absolutely memorized. And the graph of the absolute value function is kind of interesting. In fact, I think it's worth reminding ourselves of the piecewise definition of this. This is our single library function that has a piecewise definition. And the library function is equal to x if x is greater than, and we'll go ahead and say, or equal to 0. And it's equal to -x if x is less than 0. What does this mean? That means for x values to the right of 0, those are these x values right here, this graph should look like the identity function f of x equals x, which is something that we saw in our previous video. So notice for positive x values, and for 0, I guess, the graph of this function resembles the identity function. But for negative values, the graph is the graph of -x, which is the graph of the identity function reflected over an axis. And we see that true for these negative input values. If x is negative, then we graph -x. So there's the graph of that piecewise function. I like to, or excuse me, well, it is a piecewise function, but it's specifically the absolute value function. I like to remind myself that the graph of the absolute value function forms a V. We've got the name absolute value. But it's more important that you begin to connect this piecewise definition. We've been studying piecewise functions a bit. It's more important that you connect that piecewise definition to the graph of this absolute value function. Just as before, if we want to be more careful, we can go ahead and point plot. The absolute value of 1 is 1, and the absolute value of 6 is 6. So there's the ordered pair 6, 6, and the ordered pair 1, 1. The absolute value of 0 is 0, or put another way, because those values all are positive, or 0, we simply give the identity. We return the value. And then if we were to look at, say, f of -3, that's equal to the absolute value of -3, which is equal to -3, or 3. And so when we plug in -3 into this function, it spits out the value 3. -6 spits out 6. And there we've got a nice careful graph reminding us that the graph of the absolute value function forms that V shape. Notice that this function is not always increasing. It's increasing on 0 to infinity for precisely the positive values, and it's decreasing on -infinity to 0 for precisely the negative values in the domain. This graph is even, so let's label this over here. There's the ordered pair -6, 6, and so we see that when we plugged in opposite domain values, we got out the opposite range values, and that's the hallmark. Excuse me, we got out the same range values. Let me say that again, folks. I said that a little fast. When we plugged in opposite domain values, we got out the same range value, and that's the hallmark of what it means to be an even function. And even functions have that property that they're symmetric about the y-axis. I'm not going to do this usually, but you could draw an axis of symmetry here, and if you reflect this point over the axis of symmetry, or if you reflect this point over the axis of symmetry, you land back on the graph. And then finally, this graph has a local minimum at 0, 0. So there we call this a local minimum. Okay, folks, that's all for this video. I'll see you in the next one where we finish up the library.